Hello everyone, welcome to organic chemistry tutorials. Today we'll be talking about alkene addition. So alkenes are molecules with at least one carbon-carbon double bond. And addition reactions are essentially the reverse of elimination reactions. Delta H is negative, so we have an exothermic type of reaction. And delta S is also negative, so we have a decrease in entropy. And during an addition reaction, a pi bond is broken so that two atoms or polyatomic ions are added across the double bond. So in this case, I have my alkene, and I'm adding two arbitrary atoms across the double bond. So some addition reactions follow Markovnikov addition while others follow anti-Markovnikov addition. Markovnikov addition is where the heavier atom or polyatomic ion is added to the more substituted carbon. Anti-Markovnikov addition is where the heavier atom or polyatomic ion is added to the less substituted carbon. And both types of addition are known as regioselectivity. Alright, so let's do two examples. The first one is going to be Markovnikov addition, and I'm trying to add HBr across the double bond. So this is my more substituted carbon because it has two methyl groups attached to it, while this carbon only has one methyl group. And so in this case, the bromine is attached to the more substituted carbon, and bromine is heavier than hydrogen. In the next example, I have anti-Markovnikov addition, and now, as you can see, bromine is added to the less substituted carbon. If stereochemistry is relevant, some addition reactions follow Syn addition while others follow anti-addition. Syn addition is where both atoms or polyatomic ions are added to the same side of the plane. Anti-addition are where the atoms or polyatomic ions are on opposite sides of the plane. And Syn and anti-addition are known as stereospecificity. So let's look at an example of Syn and Anti Addition. So I'm trying to add water across the double bond, and in Syn addition, notice how I can have both the hydrogen and the hydroxyl group on a wedge, or I can have both of them on a dash. That indicates that they are on the same side of the plane. In an anti-addition, notice how they are on opposite sides of the plane. So for the rest of these lecture series, I will give you a bunch of reactions, and I'm going to ask you to memorize whether it's Markovnikov or anti-Markovnikov, and whether it's Syn or anti-addition. You also have to memorize the reagents. I know this is very unintuitive, but that's how it is. So some reactions will not be Markovnikov or anti-Markovnikov, and some reactions will not be Syn or anti-addition. And we'll talk about that once we get to them. So the first reaction is hydrohalogenation, and as its name suggests, I'm going to add hydrogen and a halogen across the double bond. The reagent that's relevant is simply the hydrohalogen. So in this case, all I have to write is HBr. And as you can see, in this case, it will follow Markovnikov addition because bromine is added to the more substituted carbon. So hydrohalogenation will follow Markovnikov addition if no peroxides are present. It will follow anti-Markovnikov addition if peroxides are present. So in this case, notice how I have a peroxide, which is given by ROOR, and notice how the bromine is added to the less substituted carbon. So hydrohalogenation follows neither syn or anti-addition. However, if you get a new chiral center, you will get a racemic mixture. So in this case, I'm adding HBr across the double bond, and I have no peroxides. So I will get Markovnikov addition, and you can see that because the bromine is added to the more substituted carbon, but because I have a chiral center right here, chiral center, and I have a chiral center because I have a bromine, a methyl group, an ethyl group, and a methoxy group added or attached to my carbon, so that's 4 different things, so that means it's a chiral center. I can get both enantiomers. So these are enantiomers. So let's discuss the mechanism for hydrohalogenation, and it's actually super easy. So step 1 is proton transfer with my pi bond acting as a base, and step 2 is a nucleophilic attack where my bromine attacks the carbocation, and that's basically it. The next reaction is acid-catalyzed hydration, and we're going to add H and OH or water across the double bond. So the reagents are either going to be listed as hydronium, or you could see it listed as dilute sulfuric acid. So be on the lookout. They both mean that this is acid-catalyzed hydration. So acid-catalyzed hydration will always follow Markovnikov addition, and similar to hydrohalogenation, it follows neither syn or anti-addition. But if you get a new chiral center, you will get a racemic mixture. So the mechanism for acid-catalyzed hydration is very similar to hydrohalogenation. So the first step is proton transfer, where the pi bond acts as the base and hydronium acts as the acid, and this forms a carbocation. The next step is nucleophilic attack, where water serves as a nucleophile and attacks the carbocation. The final step is a proton transfer, where water acts as a base and deprotonates this positively charged group. And at the end result is that we get Markovnikov addition, and we have the hydroxyl group added to the more substituted carbon. Carbocation rearrangement can occur in acid-catalyzed hydration and hydrohalogenation. So let me give you an example. So the first step, we're going to have a proton transfer, as we saw before. And here we have a secondary carbocation. It's secondary because it's attached to 2 other carbons. Now, instead of nucleophilic attack occurring right away, what can happen is this methyl group moves to this carbocation, and what we get, let me write that this is carbocation rearrangement, and what we get is a tertiary carbocation because this carbon is attached to 3 other carbons, and tertiary carbocations are much more stable than secondary carbocations. And then we can have nucleophilic attack occur where the chlorine attacks the carbocation, and this is our final product. So part 2 of this lecture series will feature more alkene addition reactions. So that's it for today, and I'll see you next time.